Welcome to Chemistry Lover. Today in this video I will be talking about the very important photochemical reaction which is Norrish type 1 and type 2. Now in this video I will not discuss much about the questions, rather I will focus on the basics of the reaction, that is the mechanism and some important consequence of the reactions. So in case if you want questions, you can watch my another video where I solved a question on this particular topic, the Norrish type 1 and type 2 from csir-net exam. I will put the link of the video in the description section. And in the upcoming part of this video, I will also upload another video where I will solve the questions from this particular topic. So now let's start today's topic. So what is a Norrish type 1 and type 2 reaction? So it is basically the reaction of a carbonyl compound. So let us first talk about Norrish type 1 reaction. So whenever you have a carbonyl compound like this, let's say it is R dash and it is R, and now if you treat this compound with light source, that is you shine light on this particular carbonyl compound, what will happen? So if you have the basic idea of photochemistry, you will know that the excitation of this particular molecule will occur, that is the electron will excite from ground state to the excited state, or in general the molecule will excite from the ground state to the excited state. Now, and that excitation will occur between the HOMO and the LUMO of the molecule, that is from the HOMO to the LUMO the electron will excite. Now what is the HOMO of this molecule? So the HOMO of this molecule is the lone pair on this oxygen, that is the non-bonding orbital, and the LUMO is the pi star orbital. That is, when you shine light on this carbonyl compound, the n pi star transition will occur. So the n pi star transition will occur, and we can represent that like this. So by hard bracket and star. So this represents the excited state molecule, or we can also represent it like this. So you can imagine if you put electron in the pi star orbital, that is anti-bonding orbital, what will happen? So if you put any electron in the pi star orbital or anti-bonding orbital, the bond order will decrease or the bonding character will decrease. So that's why we represent here where we are trying to show that this pi bond is broken. That is, although it is not a standard representation, but we can think like this, that this pi bond is broken, and that's why we represent it by this two dot. So when we put electron in the pi star orbital, the pi bond is broken. So this is the excited state of the molecule. Now what can happen next? So if this R and R dash groups are normal alkyl groups, then if this dot or the electron on the oxygen, if it push back like this, so it can be broken, and out of that you will get, here you will get one dot and another dot over here. Now whether this R group will be broken or this R dash to be broken, that is dependent on the relative stability of the two radicals. For example, if you have a case like this where you have start butyl group over here and methyl group over here, then of course after this step you are going to get this one, right? So you are going to get this one and not the methyl radical. So you will not get this, you will get this one, tertiary butyl radical. So this is dependent on the relative stability of the radical, and this is the case of the Norrish type 1 reaction. Now what will be the fate of this particular thing next? So next what can happen? So let's say you have a group like this where you have hydrogen over here, and here you have this dot, and here you have something R group, and now another part which is removed is, let's say, this R dash group. So next this R dash can take this hydrogen, this bond can go here, and out of that you can get this ketene. So this is one fate. This carbonyl part can be converted to this ketene. This is one fate. what can be the other things? So let's say this R dash group is like this. So let's say this R dash group is like this one, where you have this dot over here, you have R group over here. So this is a R dash group. We represent this as R dash dot. Now here you have a dot and here you have hydrogen. So what can happen? This part can go and it can get hydrogen over here, and you can get alkene like this, and from this part you will get the aldehyde. Right. So these are the general things what can happen from the radicals, but actually what will happen, that is case specific, and it depends on the question which you will be given. So according to the question, the outcome of the reaction may be different. Right. So when we will discuss questions on this particular topic, things will be more clear. But nonetheless, this is the case of the Norrish type 1 reaction. Now let us see what is Norrish type 2. So the Norrish type 2 again involves the carbonyl compound, but in this case the substrate is slightly different. So let's say you have a substrate where you have R group over here, and you have a carbonyl compound which has a gamma hydrogen. So this position is alpha, this is beta, and this is gamma, and this is here the hydrogen is alpha hydrogen, this is beta hydrogen, and this is gamma hydrogen. Now, if you have this type of compound where you have a gamma hydrogen atom, and if you excite the molecule, so the first step the same thing will happen, this diradical type, and now you can see there this O dot, it can easily capture this hydrogen through this nice 6-member type transition state, and you can get OH over here. Here you will have this dot, here another dot. Now what will be the outcome of this? So it can cyclize like this to have something like this 4-member ring OH. So this is one possibility. Another possibility is, this can push here, this can push here. So out of that you will get this OH, here the double bond, and another alkene over here. Now it can automerize to give you this carbonyl. So what will be the fate? That is again dependent on the substrate. That is, if there is a possibility that this double bond is more substituted, then the double bond may form. So it is case specific. We have to study different reaction, and then we can predict what will happen. But this is the general outcome. Now, let's say you have a substrate where both possibilities are there, that is gamma hydrogen is also there, and so you can see if gamma hydrogen is there, although the possibility of Norrish type 2 is there, but we cannot eliminate the possibility of Norrish type 1, right? So now the question is, which reaction will dominate? So again, this is case specific, and the detailed discussion of this is beyond the scope of this video. I will try to discuss that in some other video. But before ending this video, let us discuss two very important aspects of Norrish type 1 and type 2, that is, what will happen to this reaction when our substrate is a cyclic molecule. For example, let's say we have this cyclopentanone molecule, and if you do a Norrish type reaction, that is, if you shine this molecule with light, what will happen? So the first step is very simple. You can see this diradical will be generated. Now what will be the fate? So here you can see, if you number, this is alpha, this is beta, this is gamma. So gamma hydrogen is present here, but to extract this gamma hydrogen is very difficult for this O dot. So the Norrish type 2 reaction cannot happen here, and it will simply undergo a Norrish type 1 reaction, that is, this fragmentation will happen. So it will basically give you this dot over here and another this one, right? So now what are the possibilities from here? So you can see now there you have one hydrogen atom. So this dot can abstract this hydrogen atom. So this bond will go here, and out of that you will get a ketene-like structure. So let me count. This is 1, 2, 3, 4, 5. So 1, 2, 3, 4, 5. So this is one possibility, this you can get, or let's say you have this one, right? So now this part can go as carbon monoxide. So what you will then left out with, you will left out with these two dot, and these two dot can combine to give you this cyclobutane. And the last possibility is, so what is the third possibility? So the third possibility is very simple. So what we have discussed for the acyclic case, in this case also the things are like the same. So here you have one hydrogen, so this dot can abstract this hydrogen. So then you will get aldehyde over this side and this double bond over this side. So these are the three possibilities out of here. So this is the case for the small ring. Now let us see what will happen when we have a large ring. Now let's say you have a large ring like this, where you have a carbonyl group over here. So then if you shine this molecule with light, what will happen? So now you can see here you generate O dot and C dot, and now this is your gamma hydrogen. So this is actually alpha, beta, gamma, delta, right? Delta, and this is actually not the gamma hydrogen, but you can see due to the ring structure, this hydrogen is very close to this oxygen, right? So it can abstract this, and from that you will get this OH. Here you have dot, here you have another dot. So these two dots can combine, and you can get this decalin, right? So this decalin you can get. Now two products can be formed, either this hydrogen and this OH can be cis to one another, or they can be trans to one another, that is trans decalin and cis decalin. And this reaction is basically a thermodynamically controlled reaction, so that's why this trans product, it will be the major product. So here we can say it is a Norrish type 2 reaction. So we can conclude that for larger ring, Norrish type 2 reaction is the dominant reaction, whereas for smaller ring, Norrish type 1 is the dominant reaction. So that's all. In the upcoming video, I will discuss about some questions, important questions on this Norrish type 1 and type 2 topic. So for that, subscribe this channel, and thank you for watching.